Hello, it's my pleasure to introduce Honda Bokaman talking about a multi-target, multi-paradigm DSL compiler for algorithmic graph processing. You are welcome to start.
Thank you. Hello, I'm Huda. I'm a PhD student at the Mohammedia School of Engineering in Rabat, Morocco, and a research assistant at Oracle Labs. And for this talk, I will be presenting a paper which sums up our efforts at implementing a multi-target, multi-paradigm DSL compiler for algorithmic graph processing. This is, of course, a joint work with the people at Oracle Labs. So in order to give a bit of context to my talk and introduce the problem that we aim to solve, let us look at a history of the GRIMA compiler architecture, which is employed by the PJX team at Oracle Labs. So the GRIMA compiler in its early stages initially targeted a Java-based shared memory processing runtime for algorithmic graph processing. This early implementation relied on several representations of code, which fixed the order of transformations to some degree, since each transformation would depend on a specific intermediate representation. And while it was possible to reorder transformations that were applicable on the same intermediate representation, it was more difficult, if not impossible, to reorder transformations that depended on different intermediate representations. This turned out to be problematic when we extended the compiler to support a distributed runtime, because we would find that a given transformation that's already implemented for the shared memory runtime is also needed by the distributed runtime, but that it cannot be reused because it depends on a shared memory-specific intermediate representation. We also note that the distributed runtime might need these transformations to be in a different order than the one required by the shared memory backend. So this has led us to implement transformations that were already implemented, which resulted in a non-modular and somewhat redundant compiler implementation. There has later been interest in targeting two additional platforms, namely a relational database platform and an experimental database in-memory engine. It is worth noting that a key feature in all of the target platforms we support is the ability to efficiently iterate over graph structures. So each target platform uses a different computing paradigm for that. For instance, we have Java multi-threading for the shared memory runtime. We have distributed asynchronous message passing paradigm for the distributed runtime. We have relational queries for the relational database, and we have database multi-threading for the database in-memory engine. So not only does our compiler target 4 different platforms with different programming languages, it also targets 4 different computing paradigms. However, despite these differences, we still see some common patterns in the generated code. For example, all of our backends generate top-level structures for concurrent iterations, and they all use similar transformations to collect and translate these iterations. For example, the shared memory backend translates concurrent iterations into Java classes, the relational database backend translates them into SQL queries, and the database in-memory engine translates them into C structures. So we conclude that there is indeed a potential to share and reuse transformations across backends, and the goal is to have a compiler architecture that allows us to efficiently do so. The natural solution that comes to mind is to have a common IR at the center of our compiler, at the level of which we implement transformations, which the backends can then use and compose as needed. Backends, of course, reserve the right to afterwards apply transformations that are more platform-specific. We define a rich concrete syntax for this IR, which we will be introducing in the following slides. However, in order to understand some domain-specific constructs, it is helpful to first posit the graph representation model that's assumed in our compiler. So we adopt the property graph model, in which vertices and edges can be associated with arbitrary properties as key value pairs. This is illustrated in the graph example that we see on the right. So we have vertices to which we associate these values or properties. For example, we have the name property of type string. We have the number property of type int. Similarly to edges, we associate an amount property, whereas other edges do not have any properties at all. This is generally helpful in graph analytics algorithms, in which we might need to associate or define constants to associate to graph elements. We also acknowledge the heterogeneous nature of real-life data, which requires which requires the graph representations to have multiple types of vertices and edges. This is again seen on the graph example. So we have vertices of type account, so that's the vertices in green. We have a single vertex of type company, as well as two vertices of type person. We also have different types of edges, so transaction edges, owner edges, and works for edges. In our compiler implementation, we explicate this graph heterogeneity. In order to illustrate the different syntactic components of our IR, I will be using the infamous PageRank algorithm. So this algorithm takes a graph input and then computes for each vertex of this graph a rank property, which it stores in an output parameter of type vertex property. It starts with initializing this property, after which it proceeds to perform a fixed point iteration, which carries on until the difference between the old and the new rank values falls below a certain tolerance. In this fixed point iteration, we have an asset for each loop, which iterates over the vertices of a graph in a parallel manner, and then for each vertex performs an aggregation across the incoming neighbors of the vertex, and uses the result of this aggregation to update the new rank value. It then computes the difference between the new and the old rank value in order to decide whether the while loop can carry on for another round. So we start by introducing the core constructs of our IR. First, we have procedures as top-level structures. That is, every algorithm written in IR syntax will have to be wrapped within the main procedures body. The user can also define local procedures. However, there is no syntactic distinction between the main procedure and any local procedure declarations. The compiler simply assumes the first procedure declaration it encounters to be the main one, and any procedure declarations that follow to be local procedures. We define primitive types, so that's the types that we generally encounter in most common or most general purpose languages, such as namely numeric types, int, long, double, float, as well as Boolean and string types. We have core expressions, so that's numeric expressions, numeric comparisons, Boolean expressions, variable references, and literals. We have core statements, so that's assignments, as well as Java-like control flow statements, if statements, while loops. So yeah, that's the core of our IR. Now to move to the slightly more interesting domain-specific constructs, starting with types. So we define a dedicated graph type, as well as dedicated graph element type, so that's vertices and edges. We also have the aforementioned property type, which the user can use to sort the results of the algorithm or associate values to the graph elements. And we have the collection type, which is not illustrated in this example. For domain-specific statements, we have graph iterations, which allow us to iterate over the elements of a graph for each loops or BFS traversal. Sorry. We have property updates, which allow us to write a value to a property associated to a vertex or an edge. For domain-specific expressions, we have aggregations, which allow us to aggregate values across the elements of a graph or a subset of a graph using a reduction operator, namely sum, average, min, max, and such. We have property accesses, which, as the name suggests, allow us to read the value of a property associated to a vertex or an edge. And we can separate between graph expressions and core expressions using let expressions. So say we have an expression at the level of which appears a domain-specific construct, namely an aggregation or a property access. We first assign this domain-specific construct to a local declaration, and then we replace it in the main expression by a reference to this local declaration. We revisit this. I now realize that it should say rank val here. I do apologize. I was saying that we do revisit this core/domain-specific separation later in this talk. However, I can already explain that it allows us to simplify compilation, since core constructs are generally easily mapped to their semantic equivalents in target languages, whereas domain-specific constructs are more complex to translate. At the level of our intermediate representation, we design several normal forms. Now, to understand what we mean by normal forms and what role exactly they serve in our architecture, let us look at these two equivalent representations of PageRank. Do note that some chunks of the algorithm have been omitted for simplicity, but you will recall that at some point of the algorithm we have a parallel for each loop. On the representation on the right, this for each loop is extracted as a top-level structure outside of the main procedure's body, and then invoked at the corresponding position through a call to this structure. I do reiterate that these two representations are semantically equivalent. However, one is closer in shape to the generated code. So earlier in this talk, we explained that backends tend to translate concrete iterations into top-level structures. So by having a normal form or by having a representation that enforces this shape, we bring the program closer to the structure or the shape of the generated code. So that's exactly what we aim to achieve by using normal forms. We can define a normal form by saying that it's a subset of a language with certain syntactic restrictions applied. For every program, there exists at least one semantically equivalent program in a given normal form. A program may conform to more than one normal form simultaneously. Normal forms allow us to enforce certain shapes of code, embrace abstractions that align with the target platforms, and disallow abstractions that are semantically more distant, and therefore close the semantic gap that exists between the DSL and the target platforms. In the following slides, I will be enumerating the normal forms that we designed for this IR, starting with the one we just saw in the example, top-level iterations. So in this normal form, concrete iterations cannot be inlined within the algorithm. Instead, they're extracted as top-level structures and then invoked through calls to these structures. This decreases overhead and simplifies implementation, as most backends require iterations to be extracted in order to generate corresponding structures. The next normal form is explicit memory management. So in this normal form, all output properties or temporary properties, as well as collections, have these dedicated statements that explicitly allocates and deallocates memory. This simplifies code generation, since backends now don't have to analyze the entirety of the program to find properties or to find structures for which to generate relevant memory management code. The following normal form is explicit type information. In this normal form, all variable references or calls are preceded with these annotations that give explicit semantic information. So for variable references, these semantic information or semantic annotations indicates whether the reference in question is a reference to a local variable or a parameter, and then indicates its type. For calls, or semantic information indicates whether this is a call to a built-in function, a local procedure declaration, or an iterator, and then gives its signature. This allows us to have direct access to semantic information throughout the different transformations that the program undergoes in the compilation pipeline. The next normal forms is single issue iterations. This normal form is mostly needed because of a database backend restriction and relates to how graphs are stored in the database. So in this normal form, iterations can only have one output. That is, they can only update one property or perform one aggregation. We can have a combination of property updates and aggregations on the condition that the aggregation is nested within the property and that its resulting value is used to update the property. We have explicit table iterators. So I did explain earlier how graphs are often heterogeneous in nature. One way in which we acknowledge this heterogeneous nature in our compilers through the explicit table iterators normal form, in which we explicitly iterate over the different tables of the graph. And then for each table, we iterate over its elements. This normal form is mostly needed for backends which rely on a tabular representation of graphs. So that's namely the shared memory backend and the relational database backend. Finally, we have privatization. This normal form is needed by backends which distribute iteration workload across multiple threads. So in such a backend, we would need an extra or an additional effort to organize the different workloads computed by each thread. So it introduces a variable in which each thread can store its computed value And then these values are aggregated and assigned or stored in the global output variable. This slide recapitulates the different normal forms as needed by each backend. We can observe that some normal forms are required or are beneficial to all backends, such as the top-level iterations normal form, whereas others, like the single-issue normal form, is really specific to one backend, here the relational database backend. Now we move to discuss transformations in relation to normal forms. Normal forms act as prerequisites for transformations. Backends can compose these transformations into a single multi-stage transformation, in whichever order or combination needed. So this way, we break down the gap that exists between the DSL and the target platform into several smaller gaps that are bridged by these transformations. With regards to normal forms, we distinguish transformations that establish a normal form N, transformations that preserve a normal form N, or transformations that break the normal form. Once again, we have a slide which recapitulates the different transformations we implement at the level of our IR at this stage and indicates for each normal form whether the transformation establishes it, preserves it, or breaks it. We implement our compiler using spoofx, a language workbench for implementing textual DSLs. So spoofx provides a number of meta-languages which we use to implement our compiler. We organize our compiler components in hierarchical, I do have a problem pronouncing this word, but you do get it, modules. This is only possible because spoofx supports some modular implementation in all of its meta-languages. We have found this extremely helpful when developing, maintaining, and extending a compiler because it has allowed us to, for one, have a concrete separation of concerns between core concerns and domain-specific concerns. It has allowed us to, it enables maintenance because one can easily find their way across the compiler code without necessarily being very familiar with it. It has also allowed us to extend the compiler to target new backends, since the new backends targeted can be implemented without affecting existing implementation. Moreover, we can extend the code in the same or in one single component by simply adding new modules and having them import existing modules. So all in all, spoofx has enabled us to have an efficient, modular, and easily extensible architecture for our Greenwald compiler. I believe this concludes my talk. I will now be giving room to any discussion or potential questions. I thank you for your attention.
Okay, thank you a lot for that.
Thank you. I will move to the Ermite slide so I can see any questions in the chat.
Is there any question from the audience? So you mentioned that you use spoofx to do the implementation.
Yes.
Did you encounter some difficulty in spoofx in addition to the benefit that you mentioned?
I mean, there have been some challenges which we actually address in a future paper. But still, we do think that spoofx has been managing very well to meet those challenges. For example, there are some requirements in using compilers or in using language workbenches in an industrial setting that have to do with dependencies. In case of a vulnerability that appears in a dependency, there needs to be a version upgrade to address it. It also needs to ensure that any third-party dependencies use valid licenses, things of the sort. However, throughout our experience, we do think that spoofx has been doing a notable effort to meet these challenges. There have been frequent version upgrades, so yeah, it has been a good experience, if I dare say.
Okay. So if there is no other question, the next speaker